Alright, time for another DraftPhysics.com video presentation. Lighting's a little poor, but anyway, it'll have to do. So there appears to be a misunderstanding, and it's happening in physicist Michael's comment section now. So the bass and bass guy, I think it was him, who left a comment on my video saying I mischaracterized something, blah, blah, blah. And I really didn't. So you can just plainly see in the original live video, physicist Michael predicted, for erroneous reasons, he gave us the prediction for dropping a hunk of clay on the lever. Now, why that would even be a theoretical possibility, I have no clue. So in saying that it would only leave with half the velocity, he was describing the circumstance where you drop something deformable on the lever, I guess. I don't know. See, it's all based on this misunderstanding between the idea of elastic and the fact that you can have two kinds of elastic. You can have hard elastic, where things bounce, and you can have spring elastic, where things can bounce. But one of them is storage, and one of them isn't. So it's a huge difference. And that's part of where this misunderstanding comes from. Now, clearly what I'm argued, and I argued in the live video, I pointed out how I don't care about bounce. Bounce just means you're wasting the energy. So from my perspective, it has to stick in the sense that it has to lose its energy going in, or it's not going to be able to get the energy going out. If you still have energy left over, a reflection, then you didn't absorb all the energy, and obviously the other object's not going to leave with 100% of the velocity. So, I think that was all clear. But anyway, let's just say it's a misunderstanding, because in a subsequent video, Physics Michael clearly does state, in this video, modeling a lever launcher, and kind of late in that video, he does say, yes, if you have the two at equal distance and you drop one, it will produce 100% of the energy on the opposite side. Now, even though he clearly said in the first video how you can't do that, you can't have energy going in different directions. You can't have energy going in this way and have energy come out that way. I guess he's changed that view, or whatever, modify, I don't know. Like I said, maybe it's just over the stupid semantics of elastic and inelastic. And as I stated right from the beginning, I don't even want to talk about frickin' inelastic, elastic collisions with a lever. It just doesn't make any sense. So why would I even entertain that subject? But anyway, he clearly does say here that if they're equal masses and they're equal distance, that all the velocity will be put into the second object. So I was wrong to say he predicted inaccurately, because, well, in one of his predictions it was wrong, but in the revised prediction, let's say the more serious prediction, the later prediction, he predicted something different. Now, it doesn't change the fact that, I've already pointed out that the lever oscillates with the uneven masses just fine, that there obviously has to be the same amount of energy on both sides, blah, 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 and such. So it's just a matter of time, before this equation will be found wanting. And it's really already loses. So, I've pointed this out before, but there is one video out there. All right, now, so I'll leave a link to the video, just because why don't one of you people who are defending this theory do the frame rates on this video, and then you can tell us all what the truth is, because it's really the same rules apply to a Newton's cradle. So you should be able to do this extra velocity thing.
As in the
So this guy just does the calculations. He doesn't do the measurements. So he doesn't prove it. He just states it. All right. So it's slow motion. It's it's probably good enough to do frame rates on, and see if you're getting to 133 momentums in the other object. Now, from my view, it seems kind of obvious that you're not, but whatever. So I'll just
This
play this
repeats
part.
until damping the.
So when it hits, it bounces back a little, which you'd expect because they're uneven masses, and you get some of the energy into the big ball. It doesn't go very far, but it goes.
Motion of the system.
Okay, and you got to understand that it's also moving in gravity, so it's not going to go as far because it's going up as it goes sideways. But that should be calculable to some extent. And then when they hit again, all of the energy goes back into the small ball. So you're sort of stuck with the logical conclusion. How can I restore the momentum if I lost momentum hitting the ball, or if I gained momentum? If I gained 133, how can I lose it? So, it's pretty clear I didn't get 133 back. So when the ball swings away with 133, doesn't it have to come back with 133? And if two things hit each other, they don't lose momentum because they're not denting or deforming. So whatever motion there is after the collision should reveal the fact that you have 33 hitting 133. That's what this collision is. It's 33 hitting 133. And the result is you only got back 100. So if we just say 100 went in, you're saying your math says 133 left, momentums, 33 went backwards, then they went like this. So you have 33 coming this way, and you have 133 coming this way, and somehow you only get 100 back. You get it? It can't be true. We know that's not true. We know Newton's cradles conserve momentum. We know if I do the experiment without them colliding first, and I just have something with 33 and something with 133, and I hit them together, the momentum's going to be conserved, and I'm going to end up with 166 total movement. But we don't, as this reveals. So now the single ball hits the solid ball that's stiff. The same thing happens again. The stiff ball leaves, the little ball moves backwards with 133. This is a 1 to 3 mass ratio. Can you see this? Yeah, you can. So right there. This ball's stationary. This ball has all of the energy now, and it doesn't appear to have any 133 plus 33. It appears to have just what it started with. And it just goes on and on like that. It's pretty much like the coupled oscillator, which I'll show some video of because that's sort of what I did today. I played with it again. And also, I did create a catapulting device. And it's really simple, okay? And unfortunately, I did film it, but it was out of the camera's range. So, can't show it to you. But just preliminary looking at it from my observation of what happened when I did it, it looked like Brozo's billiard ball experiment. It looks pretty much like the half mass is going twice as fast. It doesn't look anything like 0.4 faster. So it's a lot faster than 0.4 faster. So we'll see once that's finished. But again, this equation only seems to work with air carts, or carts manufactured for the purpose of doing this experiment, this one specific experiment, but it doesn't seem to work with a Newton's cradle. So, and don't you think if it did work with a Newton's cradle, they would have discovered that before the air track thing? I mean, why bother investing in an air track when you can demonstrate the same exact thing with a simple Newton's cradle? I mean, why spend $5,000 on a fancy air track when you can do it with a Newton's cradle? So I think it's kind of obvious. It probably doesn't happen with a Newton's cradle. I think it can't happen, frankly. I don't think it's theoretically possible that it could happen. All right. And so what's the argument going to be? That if I put springs in here, that somehow it will happen? That the spring will magically create the extra energy? I don't think so. All right, the extra free momentum. So let's understand, this is what I call the free momentum experiment, where they crash a light thing into a heavy thing and they make extra momentum in the system. All right, so where do I want to go from here? I'll have to think about that. That's right. I was going to draw the simple. I decided I like the idea of doing the catapult experiment because we don't have to worry about all of the complexities of the sources of the things stealing the energy. So the problem with the idea of just putting a force into a lever and having it push the force out is you have to move the lever. The energy, it has to move the lever. So the idea of a catapult, where you just use the same energy to swing objects, so you're doing the same thing, okay, the lever is going to be doing the same thing, it's just pushing the objects, but this time the energy to do it is already built in. So your losses to the lever are for both experiments the same, so you don't have to worry about them, and so you can see a 100% difference between, you can see a clean difference between the heavy mass and the light mass. So what I did was I had my kind of sledgehammer thing. So this is the handle of the sledgehammer. Just have a bar, okay? And, it worked out kind of simple. I put a board behind it, and I just have a rubber band tied to here and here. So I'll draw that like that. And so this compresses, and then I put a string on here. Okay, so I'm pulling for the rubber band to stretch is this way, and so then I put a loop of, there's a screw in here, and I put a loop that's the same size around here, and then I cut it with scissors, okay, and to make a quick release, and basically just put the heavy mass here and the light mass here. And from preliminary observations, it's clear this is going really far, and this ain't going so far. So it seems clear that the velocity is pretty much twice here. But I'm just saying that, but it looks like it can often be deceiving. So I'm making no statement because I can't show you the video because, the camera did this. You can only see this part. So it only shows one experiment, not the other one. So I have to fix that, and frankly, the range is pretty far, so I probably should change the camera angle so it's going this way, and so it's a different, be better to videotape it in a better form. But I'm just saying, I think this experiment is better than the lever experiment because all of the places you could lose energy, the fulcrum, the lever bar, all of that stuff is eliminated as a variable. So it doesn't matter anymore, and you just have the comparison between 1 unit of distance and 2 units of distance and 1/2 mass versus a full mass. So it's a pretty good way, I think, of doing an experiment. And the fact that I'm using pendulums means I don't have to worry about rotation, and I don't have to worry about friction. And so all I have is the fact that it's a parabola thingy. And the movement won't be perfectly to 1 in terms of distance. Now the fact that it is 88 inches is a huge advantage because the longer it is, the longer it takes before you start lifting at a severe rate. And so it actually will come out distant-wise pretty close. This should go 1x the distance that this goes, 2x the distance, because your arc is kind of flat here for 88 inches. It's all kind of flat. All right, so that's where it is. And so we'll just do some, whatever you call it, coupled oscillator stuff I observed playing with that today. And so I have to see if those videos will properly mount. Where the hell are they? Yeah, they're gone. That's where they are. Okay, all right, got to pause and fix that. All right, back. So, so it certainly would be interesting to get physicist Michael's a prediction for the function of an uneven massed coupled oscillator. But I mean, the trick is to do the math. You have to know the spring constant and all that kind of crap. So, to some extent. So what I observed, I'll just play this. It's quite interesting to me. I mean, this is probably stated somewhere, but I just can't find any video that takes any of these subjects seriously. They're all made for kids, or there's in some other way just superficial. None of them actually go into anything meaningful about the function and whether momentum is actually being conserved. Now, I'd say there's no choice that the momentum has to be conserved, that when all of the energy is in one of the objects and the other object is still, all of the momentum has to be in the other moving object. And when this object goes still, all of the momentum has to be in the other object. It can't be somewhere secretly. There's no secret place for it to hide. Now, before I did have a weight on here, okay? And the difference the weight makes is it speeds everything up. It makes things happen faster. So the transfer from one side to the other side is in bigger chunks of energy. And so that's what I found to be very interesting. So this is a very loose rubber band with no weight on it. And you'll see what I observed, which is really quite interesting. That it takes, I didn't count, but maybe 10 oscillations between transfer. So before, when it was transferring after 3 oscillations, there'd be 3 oscillations, and then the energy would move to the other side, and then the energy moved back to the other side, and it was every 3 or 4 oscillations it would switch from side to side. Here it's like 12. So you just see this is slowly takes place. That's 3, 4, 5, it's still pushing the big one. 6, it's still pushing. 7, 8, starting to run out, still pushing. 9, now it's going the other way. So after 9, it's pushing the small one. So now the small one's getting pushed. But you can see it takes quite a few pushes. Let's see, the big one will stop. So you'll really be able to see that it's 8 or 9 or 10 oscillations. There, it stops. Okay, now the little one will start pushing the big one again. 1, 2, 3, 4, 5. So I mean, it's 6, 7, 8, 9, and the little one never really just perfectly stops. Now I think that's just incidental. So it's about the amount of energy you put in has to be, like in whole numbers. Like the amount being transferred each push is a certain amount. And if you put more energy in than fits as even numbers, then there's not an even number. And so one side has to not stop. So every now and then I get the force in just right, and both of them will stop completely. And but you have to get lucky. That's my observation anyway. Maybe there's some other trick to it, but that's what I've observed. So the little one's now doing all the moving, and it's slowly pushing on the big one. You can see now it's slowing down, so pushing. So I thought that was, I'll show you the other version, and you'll see the huge difference in how fast it moves the energy. Should work. Alright. So that's the other version. So you can see how much faster it's going to happen. 3 pushes, and then it starts to switch. So there's a little bit of a weight on there. So now it's pushing the big one. The big one's going to, now it just pushed on the little one. Now the little one's getting pushed. So it's like every 3 it pushes. There, now the big one stopped. Now the little one starts pushing. 1, 2, and 3, and that's it. And now the little one will get pushed. 1, 2, 3. So it just kind of has to do with how much tension there is in the elastic. So the more stiff it is, that's what the weight is providing, a little bit of stiffness. The bigger the chunks of energy that get switched from side to side. And the lighter, the less stiff the spring is, the smaller increments of energy it transfers. So anyway, I think it's interesting, and I think it's an interesting question. What does the textbook say? Now, I don't think the textbook has the answer in it, okay, but what does the physics textbook say the momentum of these two objects is? You know, what does it say when this one has stopped, which it will do shortly? And there. So when this one has stopped, what's the energy over here? And then when this one stops, what's the energy over here? And energy, I mean momentum, mv. What's the mass and the velocity? And what is conserved? Momentum or kinetic energy? I'd say obviously momentum has to be conserved. So kinetic energy can't be. And that's a telling fact of reality. And such. I mean, just observationally, it looks like this is going twice as fast, but you know, it's just an observation. Alright, so I will upload those two videos anyway, and I'll give you a link to the Newton's cradle with the uneven masses, and you know, if you want to prove something, go ahead and prove that that video is consistent with physics Michael's prediction, which is the math says so. The math says that you have 100 momentums hit the ball, you have 103 momentums leave, and you have 33 going backwards, and then 33 hits 133, and somehow you only get 100 out. So I don't think there's any rational mathematics that can do that. Nope. So anyway, till the next time, and such, and so forth and whatnot. I think that's all I got. So tomorrow I'll try to do the catapult video, and such, and so forth and whatnot. I mean, I don't think it's worth reading any of the comments in the discussion. Like I said, the whole thing is based on the fact that he did state two different things in two different videos, and clearly it doesn't change, in my opinion, the substance of what he's arguing. Just like he argued, you know, you can't make a balance out of a lever. Sure you can. But anyway, till the next time and such. I think that's really all you need.